If not, I'll text you.
She gives such good food. Okay, let's actually get started. So announcements, we have an assignment due on Wednesday. You'll be getting the sorting assignment, I guess that's tomorrow. We'll be getting the sorting assignment tomorrow as well. That'll be due next Wednesday. One thing to note is that the 8th is a week from Friday. So my goal is to have gone over both sorting and recursion. However, we will not have had time for the recursion assignment to be assigned, due, and returned to you before the 8th. So what I will do is I will reveal that recursion assignment early, especially as I start talking about recursion. We may not have seen everything, and it will not technically be due in this class until after the 8th. But if you'd like to get started on that as practice for the 8th and have conversations with me about your implementation, finding some other problems for it, I'm very open to that. That way you can have the assignment done ahead of when the 8th is as practice. So I'll be getting that to you fairly soon, but if don't panic about the actual due date of it. It will be a little bit in the future. Last time we worked on selection sort, we finished off selection sort very quickly at the end of the class, and I wanted to talk a little bit about the swap that we did, as well as the more intelligent swap that shows up in coding interviews all the time. So we've always, I'm sure you've seen swaps done with a third variable, but is anyone familiar with a way to swap two values without using a temporary variable? No one? No one has seen this done? Is there any way you can think of mathematically that you could swap two values without using a temporary third variable? You're only storing things in the two variables you have while you swap their values.
Just use list.get parentheses minlog instead of storing a temp value.
Well, if you do that, then you've overwritten it and you have two values of the same value, you've lost the first value, which is why we use the temp. Any other thoughts? How would we do that? How could you manipulate these two variables in such a way? So we want to swap what is at, so list.get of minloc and list.get of current. We want those to swap values. So in general, we're going to go through the syntax for this. Let's say we have two variables A and B, and we want to swap where they are, or swap their values. This is going to give us 3 lines. We can do this in 3 lines, just like before. You want to redefine A to be the sum of A and B. So now we have the original value of B stored in B, and we have the sum of A and B stored in A. What we want to do now is we want what is stored in B to become the old A. How do we get access to that? We'll say we want this value B to store the original old A. How can we get that from the current values of A and B? A being the sum of A and B, and B being the original B. Yeah? That's correct. So now what is stored in A and B? A is still the sum of A and B. B is now the original A. How do we get the original B to store that in A? Yeah, that's exactly right. The original A, sorry, A, what's currently stored in A is the sum of A and B, and B now stores the original A. The sum of the old A and B minus the old A gives you the old B. We store that in A. And now what used to be A is stored in B, and what used to be B is stored in A. We didn't even define a third variable and do that. So if we wanted to implement this, where what we want to swap is the values in the list at index minloc and the value at in the list at current, that becomes your A and your B in this case. So how could we do that without using this temporary variable? You just have to choose which one's A and B. Yeah, let's say list dot set. We're gonna set the value of current. So we want to set at current to be the sum of list dot get current plus list dot get minimum. So that is the equivalent of A equals A plus B. That first one. Now we want to do B equals A minus B. So we're deciding that this list dot get current is our A. So we now want to set to the other. So we're going to list dot set minloc. So at minloc, we want to set it to be the current A minus B. So we want to say list dot get current minus list dot get minloc. Finally, we want to do, once again, now it's A equals A minus B. So we will list dot set current to be list dot get current minus list dot get minloc. This looks way more complicated. Why might you ever want to do this instead of that? Yeah. Yeah, we don't ever have to initiate or initialize or do anything with a third variable. If you have limited amounts of memory, or if you're working on some kind of embedded system where your memory is your cache on your CPU, where you don't have very much of it, then memory is at a premium. If you're doing something as simple as a swap, you don't want to utilize resources that are unnecessary. So this is, again, a common interview question is, can you swap values without using a third variable? And this was one of the ways to do that. Yeah.
Let's work with strings.
Will it work with strings? Since strings have an underlying representation as a character array, if you have a unique way of going from a list of characters that have values, converting them to a number such that that number can be removed and figured out, so that is possible, then you could do that, but you would have to write that functionality yourself. Just like a number is unique in its digits and its value is a representative of that number, so thinking in base 10, like the number 123 is 1 times 100 plus 2 times 10 plus 3 times 1. You could do the same thing with a string, depending on what all the legal characters are. So you could convert each one of those string characters into their ASCII values. And then you could do the first value times something, the first value times something, the second value times something higher, the third value times something higher. And as long as that multiplier adheres to some kind of base system, so it could be base 10, base 2, doesn't matter. What you create is a number that can only be recombined in that system into that one string. And then you swap those numbers, do the reverse to get the string back from the number, and you would have swapped without that variable. You could do it, you just have to know how strings are stored underneath of it. All right, so now we're going to test this.
Should we comment one of those out?
Yeah, it's exactly what I'm gonna do. It's exactly what I'm highlighting, just to make sure that one of these does in fact get highlighted or commented out. Here's our main, we're gonna run that. We just go ahead and run this file, and once it saves, you see that it doesn't do anything. We added it and then we printed it. We should probably actually sort it after we do that. So we're gonna call selection sort on nums. And then we're going to print it out again. There's the before, there's the after. It added a 0 somehow, interesting. Turned 19 into 0. An issue with this. There'll be one thing. And I don't have the capacity right now to figure out exactly what that is and or why. I'll figure this out, and when I upload it, it'll be correct. So today we're gonna start the next one, the next sort. So with a temp, this works just fine. It's assorted and in order. Does anyone have questions about selection sort before we move on to the next one? We're gonna move on to the next one. Actually, we shouldn't do that yet. We should talk about the complexity of selection sort. Worst case performance of selection sort, what do we think? Yeah,
N squared.
n squared, what makes you say n squared? That's absolutely right.
We have nested for loops and they both just depend on the size of the list.
Yeah, that ends up being perfectly correct. So if we're looking at exactly what this is doing, the very first time we sort and figure out what goes in the first position, we have to make n comparisons. We make an assignment and then compare to every element in the list. The next pass through, we're going to compare, but doing it with n minus 1, n minus 2, n minus 3, n minus 4. So we get a sum that looks like n plus n minus 1 plus n minus 2 plus n minus 3 all the way down to 1, which is just by the commutative property of addition, the same as 1 plus 2 plus 3 plus 4 up to n. We determined that was in order n squared, so this is in order n squared. And again, I report big O because as far as we know, there could be some order that allows us, there's not. This really is a theta of n squared. But if we reported it as O of n squared, then we're saying that is an uppercase bound. Yeah,
So you're saying it should be theta because the big O and the what's the symbol called?
the omega.
Omega are
Mhm.
the same, so it's the type bound and therefore.
Yeah. Well, yeah, it's a type bound here on the worst case performance. We know that the worst case is going to be n squared. It's not wrong to say big O of n squared, but since we have more information, we know it's a type bound. We could say that it's theta of n squared. What about the best case performance? Is there a way that we could order this list such that selection sort is more efficient? It's already sorted. If it's already sorted, how many operations are we saving? It's usually a great idea. Pass in on a list that's already sorted and there's less work to do. But according to this algorithm, it turns out that we're still going to do exactly the same amount of work, even if it's already sorted. To know where that lowest value is, we don't know where it is, that it was in the first place we looked until we've looked everywhere. Well, it would be nice if that mattered, right? If we could have a way of knowing we're currently looking at the lowest value, there's nothing that we need to do. But we'd have to actually go verify the structure of the list ahead of time, which only matters if the list is already sorted. So selection sort does not do that. So its best case performance is also n squared. What's nice about this is now we can ask about the average case performance and we don't have to calculate anything. The reason is if the best case and the worst case are in the same order, the average case cannot vary from that order. It wouldn't make sense to have an average case that's in a different order than the best case and the worst case that are in the same order. That doesn't make sense. So the average case is also n squared. Is that intuitive to people? Do we see why it is quadratic across the board? Can draw it out a little bit, sure. So in the best case, let's just say we have some list. We're always, no matter what we're doing, going to be doing exactly the same amount of work. It doesn't matter what the structure of this array is. It could be going from lowest to highest or highest to lowest. According to the algorithm, if we actually go through that process to know that we know where the smallest value is, we have to look everywhere. How much work is that going to be? We have to look at n cells. Eventually, we find where that is. We go, great. We have located the smallest value. If it's in order, then it was the first thing we looked at, but there was no way to know that for sure. After we've done that work, we found this value. Then we need to go for this and do all of this work. For this, we need to do all of this work. For this, we need to do all of this work. So it creates an n plus n minus 1 plus n minus 2 all the way down to plus 2 plus 1. And one of the ways I'm going to draw this out is kind of like a triangle where we can break this down now into this amount of work is n. So this amount of work is now n minus 1. I'm actually going to draw it in this. This is n work, this is n minus 1 work. This is n minus 2 work, all the way down to where the amount of work is 2 and 1. So you get a sense of kind of the area of this pseudo triangle. That's not exactly a triangle, but as this got more denser and denser, it would start to approach a triangle. So anything that is n squared is going to be representable in terms of a two-dimensional visual graphic. And we'll see that the size of this is n because this length is n, and the size of this is also n because how many elements do you have counting up from 1 to n? You have n of them. So the area of this pseudo triangle as it expands is going to be based on the size of n, where we have two variables. We could increase that and we could increase that. But since they are both n, we have to change them at the same time. If we add 1 to our array, it adds an additional row and an additional column for every row. So as we stretch this triangle or compress this triangle, with the one variable we have control of, the size of the list, it ends up having a two-dimensional effect on the number of operations that we need to do. So you can imagine there being like little handlebars here that allow you to pull down and pull out at exactly the same rate, but that's it. You can't operate them independently. You can only operate them at the same time. That expands or contracts this triangle, and it stays in a triangle shape, but it just gets bigger and bigger or smaller and smaller. And that would be the same thing as expanding and contracting our one-dimensional list. It's just that we have two variables, the list size, and how that correlates to the amount of work that has to be done to sort that list with selection sort. Sometimes, depending on the order of numbers in your list, this will be able to be represented differently. And so you'll get something like, this is the worst case, but the best case looks different. However, the best case doesn't look different in this case, because even if the smallest number is right where we look first, we still have to look at everything to know that it's in that first position. So that means there's a constant amount of work to do here, regardless of the underlying structure of the array. Yeah,
Is there a way to check if something is sorted that's faster than override?
no. You just have to go through and say, are you less than you? Are you less than you? Or yeah, not much you can do there, because you have to look at every element. Even if you were to use something like a binary search to say, is the middle, all right, we have the middle element. Is the quarter element less than the middle element? Is the other, eventually you still have to look at every position, because it could be that everything else was in order, except for that last place that you looked that was out of order. Not much you can do about it. Good question. Other questions before we dive into insertion sort? Yeah. So when is the question, when would we have used that instead, or what? We're using kind of worst case analysis on each of these that says that this O says that we've identified that it's possible that this could be better, but it's not going to be worse than this. We've basically proven that this much work is possible. We look at selection sort and we see it's quadratic. Could it be linear? Well, actually, no. So really, these could be thetas. But big O allows us to say, if there is a more efficient solution that we just haven't discovered, that's fine. I guess there isn't, which is why these should be thetas. But the big O just, yeah, it errs on the side of it could be more efficient. It's not though. All right, to insertion sort. Since I'm doing these out of the order of what we have here, I'm just going back to, I had done insertion sort first before and then selection, but I find selection to be the most intuitive. That's just me personally. I'm actually curious if you find any of these to be more intuitive than the others. Usually there's a little bit of dissent in the ranks about which sort is the most intuitive. So let's take a look at the pseudocode of insertion sort. All right, we're going to start by saying the first element in the array is sorted. We're going to start looking at every element past that first one, and we're going to be storing it and then moving it backwards into place where it goes into the sorted list. So the element at position 0 is sorted. The element at position 1 is the first element that is not sorted. We're going to start to move it backwards through the array until it reaches a place where it is sorted within that subarray. So we're either going to keep element at position 1 there if it's larger than the element at position 0, or if it is smaller than the element at position 0, we're going to swap what's at position 1 and position 0. When we are done with that process, what's at position 0 and 1 are sorted with respect to each other. Everything at position 2 and later, we have no idea about. Then we're going to grab position 2 and move it back through either swapping it with 1 and or swapping it with 0, or neither of those, so that we get 3 elements in a row that are in order. And we grab the next one, and that's going to be moving back. So we're inserting the current element where it goes in the sorted list that we are building. Yeah.
Draw a picture.
We're definitely drawing a
So
picture.
lost.
We're drawing a picture. So yeah, extract, that just means kind of store it off. And then starting where we are, moving all the way down, we're going to be swapping each position or making space until we can take the value and put it where it goes. So let's draw out an example. About 6 elements. Good enough. Some of those are looking a little more like rectangles. Let's get 6 numbers, shout them out.
6.
Well. 2.
12.
6.
19.
Alright, something a little more interesting than the. You'd be surprised how frequently classes, the largest number is the last thing that they say in a sorted list or when going through a sorted list. So usually I make 1 or 2 changes. I like that there's a duplicate. That'll make things interesting. So now we want to sort this. I think this will earlier on show what's going on. So we are going to say that congratulations, we're starting with this element gets a gold star, blue star. It's sorted. Yay, with respect to itself. We are ignoring the rest of this as an array of size 1. This is sorted. Do we agree? Woohoo! We're done. That's the day's lecture. That's insertion, Duncan. So now we're going to extract this 6. So we're going to, by extract, we're kind of going to store it off in this variable that I guess we'll just call the current value that we're looking at. Now we need to march down the array, making future space for this 6, swapping it with everything that is larger than it. So the question I have now is the element that is before it larger than that 6? Yes. So we're actually going to overwrite this 6 with this 19. So this goes here. Even though there's a value here, this 19, it's really a whole. Question?
Is it really overwritten when you have it sorted, period?
This, at this position, yes, we do have the ability to access it, but that's why we needed to store it up. That's why we needed to extract it, yeah.
I think that does answer my question, actually.
Good. 2 questions with 1. I'm in a weird mood today, apparently. So now that we're at the beginning of the list, that is one of the termination conditions for this down to the last sorted in, so down to 0, all the way to the beginning. So there's a break in here that by the time we see something that's less than, then we're going to take the 6 and put it there. Unless we get all the way to the end and that's where it goes. So with this whole, since we're at the beginning, we're going to put the 6 there. And this becomes our new sorted array. Do we agree that as a 2-element array, this is sorted? So we're going to move on now to this element. We're going to start overwriting values until we reach a place where either we're at the end of the list or there's a place for that where the next element is less than it. So is 19, so first we have to extract the 2. Is 19 bigger than 2? Yes, so we're going to overwrite. Is 6 bigger than 2? Yes, we're going to overwrite. We're at the beginning. This is where the 2 goes. Do we agree now that as a sorted list of 3 elements, this is sorted? Store off the 12. Is 19 larger than 12? Yes, we overwrite. Is 6 larger than 12? No. So now we've reached this break point, break the loop and insert X here. Where we currently are, where we would have overwritten the 6, that's where the 12 goes. So we've broken from the loop here and we need to now loop back around, breaking from this loop and looking at the next element. So now we are going to insert the 6 where it goes. Extract it, store it off. Is 19 larger than 6? Yes, we're going to replace it. Is the 12 larger than the 6? Yes. Is the 6 larger than the 6? No. Since it's not technically larger, it's equal to, we're going to break. This is where we're going to insert this 6. And we do the same thing with the 5. We're going to store it off. We're going to ask, is larger? We're going to replace, 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 replace. And finally, we reach something that we can't replace. Or that we shouldn't replace, the 2. So this is where the 5 goes. So you can see how we're moving things over, shifting where the empty place is, where the duplicate is. And wherever that hole ends up is where we want to put it. Yeah.
Wouldn't that make less work than a selection sort?
It's curious that you say that. We're going to analyze that momentarily. Keep that in the back of your minds as well. Is this more efficient? Is this less efficient? If it is more efficient, how much more efficient is it? Is it meaningfully more efficient? Is it a constant factor more efficient? Questions? So your next task is to implement this. So go ahead and take some time. My recommendation is if you're forming some friend groups in the class, get up, move yourself around, introduce you to someone new. We're all in this torture together, right? It's 9 a.m. for all of us. If you don't want to do that, that's okay too.
You read this house, it just.
Good. Good.
Yeah. So.
That always bothers me too. That's why I think like my YouTube were public. Knowledge should be public, right? I think so, right? So we make. I think so. Yeah. Right. Okay, same number.
Okay, yeah.
And then you're going to extract. Yeah, sorry, it's index. Oh, you got it.
Can't we?
And then we're going to start.
So we can get like inch element, right? And that's just our. Yes.
Well, if you want to do parents.
Yes. Here, right, when it makes one random equals to whatever the I is one, whatever the index. Additional ones. So we need to. No, yeah, you, I guess.
Actually, I guess that's totally saying.
Yes.
And then we make an adjustment.
Yeah, we've already marked the first one. And so we don't launch that.
Well, aren't we, we're.
So, since
Down, we're extracting though.
It's like.
We're not starting to something. Yeah, so we want.
It's weird, so we don't do it. Sorry, because.
And then actually, our meeting says, and our we want to go back. We want to start.
They'll have enough experience by then.
We want to start at the next one and go backwards. And see order and see.
It's just bubble.
But I don't think we need to have the right behind your head.
Next, we're doing bubble.
Yeah, it's true.
My personal least favorite.
Uh,
A lot of people's favorite.
it's also smart time.
It's actually fun to watch.
Yeah. So you're gonna mention.
Yeah.
Or second.
Yeah. That makes sense.
So what work?
Today's, we just.
You need to tell, so I'll tell you like, door off the other side, so the time could be just straight.
Is shaker.
Yeah.
Yeah.
And then if.
No.
So it looks like the data links around.
Okay, that's less
Nope.
than.
It's also.
Well, Jay.
Yeah. So, go on.
Well, I.
Sort shape start.
Okay, take it over my.
So.
Not get started. It's just like, you're getting, and having this work.
Instead of.
This one's gonna be two. And seven, and then.
Yeah.
This is where.
So we have to do. So. Yeah.
I can certainly see how it works.
Which for? Great, that's that.
I don't.
We're in that loop.
That's, I suppose, sort of exists. That's this.
And then we would say. Yeah.
And this one.
That loop, we do another one.
Like,
Yeah.
we're only,
I didn't know. It's not that. You will certainly understand.
Yes.
Yeah.
Yeah, no, it's.
We don't need this.
We want to say, okay, well. Okay.
We're gonna fix.
Very important.
But, and that's when we say.
Very huge show up.
Six, yeah.
So we'll get to.
So let's get to this. Yeah. And then maybe just go back and say.
Those two at the same time.
Yeah.
So then six.
Yes.
And then we. Go to two, we'll have to go back.
Just writing.
And then we go to 2 less than 6, so this 6. I mean, what that says. But if you need to worry about it.
We said in the camera.
I never. I got these on yesterday. Bond.
Oh, wait, the.
Where? So that's why I said.
Is there?
So the current of this one.
There.
So probably make more sense than it shows. Increment, check it before. Set it out. And then we want to set at.
A lot.
We want to set at J. So,
Hey, what document?
Yeah, so we compare it.
Yeah. Like getting to like. That's where the sales like.
And then J.
Jane.
I think
Jane is.
Then you said, well, is that just? Oh, is that just I?
Yeah.
And then we can say right now, it's a shape, so just says before it, and then it goes through that. You could set last one next.
Sorry.
It's like right now. Well, I guess oh, yeah.
I did say that's. I think about.
Like files are work.
Yeah, well, so it's on.
What we have.
Because the current is not great.
We need to store that money.
Right, so. Well, J equals element, right? Or element equals right.
So if you could, instead of ten, we should be. Very.
Oh.
A few minutes to go, how's it going?
Yeah, it's kind of set.
Making progress, getting close?
Yeah. Yeah, so we want eyes. Like, that's what your last line.
Like it's a very strong kind of, but it could be worse, right? I do.
A couple minutes, maybe at least set this up.
And then otherwise, right, we just said J. Right.
Otherwise, we say.
Because once we got to the spot for J is. Less than J minus one. But we want any server.
No. That's right, because we taken that. What was originally there, and this is-
Yeah, that's true.
So we have all of these ones that says that.
Okay.
And then,
I guess we'll see. No, no, no. Okay, thank you.
We're not gonna get too deep into this, considering we have a minute or two left in class, but. Maybe we can at least outline this in pseudocode. So this is something that I've been wanting to demonstrate for a little bit. With a minute, we can at least get started with it. So when I'm sitting down to start writing code, I don't dive right into the code and start coding. I come up with some kind of design first, and then try to fill in that design. It's not as necessary as you get more experience with something that is smaller or more self-contained, but in general, it is very useful to be able to just take a moment, design, and start to implement the design. So you can start by just writing comments, kind of like that pseudocode. So we know that we need to do something for each element in the array. So I would just start with, for each element in the array, inside of that, what is it that we need to do? We need to move it back into place. So what information do we need to be able to move it back into place? We need to extract it. Then we need to jump into, so from that element back to, so it's kind of taking what was the pseudocode and putting it in here so that I can line by line start replacing this with code. And that can help when you see that there's a comment left. Oh, right, I've forgotten something, because you're thinking about this in general from the design perspective before you're starting to write any code. So we'll finish this process off and finish off coding insertion sort first thing tomorrow. If we get to bubble sort, that would be great. Oh, bubble sort. And that will be the last one that we cover for now.